elimination. We know what the goal is of elimination, right? Take somebody out. Just kidding, not somebody, but something, right? The goal is to take terms out and then simplify the equation. But as you saw in section 7.1, some of the equations might get a little harder than you saw in algebra 1. You might not just be dealing with linear anymore. So that's why we're reviewing it, and we're going to be using substitution and elimination a lot as we get towards the end of chapter 7, and we're doing harder systems or systems applied in different ways and forms, etc. Partial fractions where we have to use systems to solve. So guys, just like in almost any chapter, the first couple sections we're reviewing and getting ready for what's coming. So, elimination, trying to make terms match. Opposite sign, same coefficient, same type of term, like x term or x squared term or y term. They're opposite in sign, so when we add down, it'll of course cancel out. Once again, if you're like, I got this, thank you, algebra teacher. I heard someone say yesterday, algebra 1, we don't even know anything except for factoring from algebra 1. Oh my goodness, the whole foundation to all upper math, including SAT and ACT and your math placement test for college comes from algebra 1. So, don't let me ever hear you say that. Okay. Well, all in good fun. Teaching moment. Possible operations. Now these are things that you can use. Technically, this is getting us ready for matrices and row reducing. So that's in chapter 8. We have many steps before then. What are we allowed to do? If you're looking at a system, number 1, if you don't like the order it's written, especially if it's a 3-equation system, you can interchange equations. You can change which one comes first or second or third. You cannot change individual terms of the equation, but you can multiply entire equations by non-zero constants, positives, negatives, whole numbers, fractions, etc. Totally legal as long as you keep it balanced, multiplying both sides of one equation. What you multiply one equation by, you don't have to multiply the others by. Each equation is independent, even though it makes or comprises with the others an entire system. And last but not least, you can add one whole equation to another, but you can do a lot more than add. You could theoretically multiply an x, but in solving systems, I've never seen that to be helpful. Yeah, I've never seen it to be helpful. Technically, in solving systems, especially weird ones with like e's and ln's and things like, not ln's, with e's, exponential type functions, it might be helpful also to multiply or divide specifically whole equations. So I'm not saying you're only allowed to add one equation. I don't know where it went. Maybe it's coming. Maybe it's lagging. Put it in the star, next to the star. Not only can you add one equation to another, you can also divide one equation by another or multiply one equation by another. Adding and dividing are usually the two most useful ones. I went to sleep. Let's see if we can bring it back to life. Hey, look, do you guys want to see the spiffy calculus stuff I was doing? Isn't that fun? It's an integral. Look at, I'm using the Y bars that we learned in our graphing calculator handbook at the beginning of the year. What else am I using? Do you guys know what this little arrow stands for? Stow it? Stow it away? Now here's what's pretty cool, Ricky. Guess where this number came from that I stowed it? See how you see negative 380 and I stowed to A and it says 15.79? Those numbers aren't the same.
They're not.
You have something like plugged in already?
Yeah.
No, I put something as A, but wasn't that number? Do you guys remember that one other place we can get numbers from our graphing calculators to stow them?
What?
What?
I would try. Oh, am I right?
Look. Who do you
Was I-
think
was I-
15 point? We did this. Does no one remember?
No.
Who do you think 15.79 yada yada is?
Is it 0?
This was crucial to the calculus problem today.
Inflection point?
The 0. And if you leave a graph, and if you immediately leave and hit the stow button, guess where it's going to put it? Wherever you want it, even if it's not the number above. Look, you kept it. That is pretty cool. Anyway, coming back. Let's see if it'll be alive. This is a bunch of.
What's almost
Where the second derivative equals 0. Big calculus. Anyway, so you can also multiply or divide. Sorry, I was using that learning opportunity as one thing was dying. Exactly.
Our desire to take calculus.
Awesome. Show you how it all goes. Or just remind you of some cool things your calculator can do. Let's go get ourselves an example, huh? This example, or this section can't be too bad. I'm writing all over you in a okay. Why on earth is elimination a good idea for this one?
Because-
Yeah,
just like through three.
The only reason we can even think elimination is because we have 5 terms. Now, could we use substitution?
Yeah.
Of course. We could solve for x squared, plug in for x squared. Don't solve for x. We have an x squared. But if you like elimination, this is totally a valid candidate. If some of you guys are thinking matrices, we can't do matrices with these guys. So, moving on. Why am I writing a negative 3x squared and a negative 3y squared? What am I doing? I'm multiplying by a negative 3 to make them match, but the opposite, them meaning my like terms, right? What's going to be on the other side? Because we have to keep a balance.
Negative 75.
Good. You can think of it as killing a seal if you don't distribute to everybody. Seal says distribute your negatives. Let's just expand it to distributing any multiplication. You have 3x squared minus 16y equals 0. Some of you would not pay attention. You'd be like, yay, so this is going to be negative 19. That's wrong. Okay.
Because it's a different sign things.
So we have to go ahead and write them separately. So be careful if you do choose to do elimination with something like this. Y squared and y's cannot combine. Is 3 going to everybody? Oh. So that's the only way to solve? Is anybody getting it all to one side?
Factoring, yeah.
Now you guys, I know many of you hate these ones with the number in front and at the end. But how do we go about thinking of factors? Oh, I moved them all so that the 3y squared was positive.
Oh.
We could pull a negative 1 to that. Don't we multiply the 3 to 75? Make it, someone check me, is it 225?
Yeah, it's 225.
But it's a negative, yeah?
Yes.
What are factors of 225 that make 16?
I'm looking.
Well, 225, isn't that 15 times 15? No,
It is.
it is, but that doesn't help us. 5 goes in 45 times?
I'm checking.
25 times, ooh, that works. How many quarters are in 225? 9 quarters. 4 and 1. You guys don't like the quarter math, huh?
No.
25 goes in 9 times. How come that's good? It works, but which one has to be negative? Mm-hmm. Remember the grouping? Now hold on, I'm writing it this way on purpose. Even though some of you, most of you probably would write those switched, and that would actually be a good idea. I would write those switched as well. I'm just showing this on purpose that we review some of our basic math. Question. Can I, in grouping, just put parentheses and say, let's go? No. Because as soon as I do that, what am I saying is going on right here? I'm saying multiplication. That's not multiplication, that's simple subtraction. Oh. So the more careful ones of us, that'd be right. No. Because the negative comes out from both of them. The negative comes out from both of them. The safer way that I would say is whenever you have a minus with grouping, add an addition. Add an addition so it's not multiplication and then group the negative. That's probably the one that will save you from mistakes. If you add an addition, subtraction is adding negative. Then we pull out a y from this guy, we get 3y plus 25. You can pull out a negative. Is that it? -3, good. Then we get 3y plus 2. It's not pretty, but we got it. It still equals 0 chilling over here. You guys remember when we have factors equal to 0, don't we set each equal to 0 and solve?
Yeah. Why is it 27 and 3?
Once we have y's, what do we gotta do?
Negative.
We'll find ourselves an x. Ugh. Where do we find ourselves an x? Plug it in there, or there, or there, or there. Who looks next to it? Yeah, maybe. You don't have to square them. Want to use that one?
Yes.
Okay, we'll go plug these guys in. 16 times 3 is 48. Add the 48 divided by 3, that's 16. Square rooted. X equals plus or minus 4. Use the 3 double check. 16 times 25 thirds. 16 quarters. That'd be 400, right? 400 over 3. Positive, negative 400 over 3. Negative 400 over 9. Is anybody else getting the square root of a negative on this side? I'm writing the negative down because that's going to be an imaginary number, I think. But someone double check my math. I'll do a pencil.
What if you make
But a negative times a negative would be a positive, right? And then you would subtract the other side. I think that's imaginary. Anybody else there? So if I plug in a negative, multiply by a negative, that'll change then to be positive. I'll subtract it to the other side and square root a negative. Yep. Long story short, this guy, he's imaginary. So our only answers come from this guy. Our final answers will be 4, 3. And negative 4, 3. Anybody catch any errors though? Please feel free. Yeah.
I got -3y plus 25 and y plus 3. Because I did not look because I was thinking 75.
You got 3y minus 25?
-3y plus 3.
I got 400 over 9. So square of negative 3 over 9.
Oh. Because you did it differently.
Oh,
I
because
moved it
I,
one.
yeah.
Yeah. First checking real quick because Tyler went ahead and graphed the equations and his is showing -3 instead of positive. 25 minus x squared square root plus or minus y equals -3x squared. Alright, we found it, we're good. Wait a minute. Did you guys shove your graphers out anyway? Have you looked at number 19 yet, or are you just chilling? What's number 19 say? Use a grapher. Well, how do we use grapher? Well, we plug stuff in. Where do we plug stuff in?
Grapher.
Yeah, but where?
Y equals,
Exactly. So, who's my y1 gonna be?
X plus fruit.
This
Yeah.
guy. Who's my y2 gonna be? That guy. But a few of you guys got a little confused maybe yesterday because you were trying to look for the y button. But remember, in our y equals menu, y has to be by itself, right? There is no other way for y to be. So when we go to our grapher, ignore the functions, these are crazy ones from calculus. But we have to have the y by itself on the left. We have to have the y by itself on the left. I'm actually setting up for calculus. I'm going to go ahead and deselect that. You guys should be graphing, but you can't graph yet until you get who by itself. Yeah, so you get y2 by itself. And you're going to graph y1 and y2, and once again, how do we find solutions to a system on a grapher? And you can pick up your notes as well. Just pick up your spiral way down here. You saw the back page, right? Did you cross out one? So what do you guys get for y2? Yeah. When you graph, how many intersections are you finding? Looks like one, but you better zoom in maybe and double check it doesn't hit twice.
But it's not X squared. Wait, which one?
But if it, remember e to the x?
Oh, are we talking about subtracting them? I thought you said what?
No, just graphing them and finding intersections. So e to the x goes like this, right? So the line could like skim. Supposed to be a tangent line and only hit once? Okay. Because it could skim, or do you see why I was asking them? Couldn't it technically like barely cross through and you have to zoom in to see it? Okay. But if it doesn't appear to do that, then I guess we just have one intersection, and where's that one intersection?
0, 1.
Oh, I think it's 0, 1.
Yeah.
Yeah.
It is.
Make sure you find the actual intersection and don't just approximate. Find the intersection.
Why does it show you
Is anybody else having issues with their calculator? How are you guys doing? Says first person. You say yes on that, yes on that. Yes means it. Alright, cool kids. What else is in section 7.2? Life just got exciting.
We got.
Oh. No.
I'm going to change the equivalent. I actually don't like what they say is equivalent. So let me change it real fast. We're going to give examples for each of these. This is actually an Algebra 1 terminology thing. So hold on, let me change this real fast. I don't like their definition of equivalent. So let's go to we'll make that our equivalent example. Kiddos, what would happen mathematically? We'll talk about what's happening as far as the graph itself. But what would happen mathematically if we're looking at the equivalent? They're the exact same, right? So this would be an example of equivalent equations. But then we're going to separate that from what it means to be an equivalent system. There are equivalent equations and there are equivalent systems. Okay? So equivalent equations would say like, hey, these are the exact same guys, right? How do I know that? Mathematically, how could I figure that out? Yeah, if I multiply this guy by -4 in order to try to make these two terms match with the opposite in sign, that would be -8, which would cancel, right? That would be +16, which would cancel. And that would be +28, which would cancel. We would end up getting 0 equals 0. If you have equivalent equations in a system, they're always going to cancel out when you try to put them together. When you have equivalent equations in a system, they're going to cancel out because they mean the same thing. They just have different coefficients, but they represent the exact same idea. Now, equivalent systems just says, okay, whatever you have as one system could show up as another system, or we could change it to be something like Y is a system. Oh, where'd it go? It just randomly disappeared? Cool. There's you. Want to talk about the calculation?
Actually,
It is a little intense. It's coming back.
let's do.
And as the notes come back up, which hopefully they will be doing soon, I wrote a system that is equivalent to the original system, and I want you guys to see if you can figure out how or why. I wrote a system equivalent to the original system. I want you to see if you can notice how or why. So to be an equivalent system, why is this system equivalent to the earlier one? Yeah. I multiplied the original equation by 3, right? Times 3 times 3 times 3. Oh, so it's the same thing, just a different form? Exactly. What did I multiply this one by?
Divided by 1/2.
So if both of the new equations in the new system are multiples of the original equations in the original systems, aka if these equations are equivalent and those equations are equivalent, then what can I say is equivalent as well?
Everything.
The system. And so equivalency just means the numbers can be different, but the meaning has to be the same in the sense of they have to be multiples of each other. And if an entire system is a multiple of another entire system, we can say they're still equivalent. Now, there are two different descriptions that we can come across, or two different ways to describe systems that we're given. Consistent and inconsistent. There are two different titles that we can give the systems, consistent and inconsistent. Now here's the weird thing, every single one of these systems, guys, don't they each have two equations?
Yeah.
So we're in the second dimension, we're just dealing with x's and y's like we're used to. But what's the weird thing when I go to try to find the lines on the graph? I see this guy intersecting in how many points?
One.
So we can call this one solution, right?
Yeah.
I see this bottom one intersecting in how many points?
0.
So we can say no solution. What's going on with this guy that only has one line?
Infinitely many solutions.
It's the same line. The systems are equivalent. When the systems are equivalent, they're going to match everywhere because they're the same thing. So we would say infinitely many. Some of this coming back from algebra?
Yes.
If not, it's back in your brain somewhere. Maybe just filed away. Let's go look at the math for consistent. Let's look at the math for consistent. For infinitely many, what does the math do? And we've actually already seen an example of this. What does the math do when we go ahead and try to make the terms match with the opposite? Everybody's going to cancel. I'm doing it fast, but everybody's going to cancel, and you're going to get a true statement. The x is gone, which shows you it's not just one solution. It's not even finitely many solution. But since it's true, we say, oh, this is one of those overlapping ones. Okay, infinitely many. For C, for the next example, for the next consistent example, what's the math going to do? So we still multiply by 2, right? what do we end up getting? I'm just gonna come down below. 4x minus 6y equals, is this the exact same equation? We should sue. That's not a consistent one. Guys, what would have to be different for a consistent one solution one? Yeah, we can do that.
The 6 is negative, and it's not the first one.
I don't like just changing the signs though for this example. I want it to match. Stupid. What is this line? This is a line with -1. Up 2 over 3. (2x minus 3y equals 3). Oh, that is one of the lines. Okay, the other line is wrong. The other line would be y equals plus 3. What's my slope? What am I doing? Down.
No,
Ew, this is
minus 1. Yeah, faded.
That's empties.
Two
He
faded.
died again.
Yes. It's 3 deaths in one day. It's a new record. Shut up, Ricky.
Is he really not coming back to life?
Dies
What did
more
we get 2 days in this section?
This thing dies more than a superhero. Superheroes have reputations for dying a lot and coming back to life a lot. We should completely underrate any emotional attachment we have to any of them.
Yeah.
Okay, you show them to me later.
What is the death of Superman? Oh no, he's back. Look at him, I guess. Doing that too.
Alright, we're almost there. Sorry, guys.
The Cap's dead.
It takes a while to
Nope,
come back.
he's back. Charles dead. Nope, he's back. Logan's dead. Nope, he's back. Amber's dead. Nope, he's back. Sarah's dead. Nope, he's back.
Oh,
That's true. Yeah. Robin's dead. Nope, he's back. 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 Robin's dead. Nope, she's dead. Loki's dead. Nope, he's back. She's back. Right, JJ?
Alright, here he is. Woo! That took a while. Alright, change your equation. Now he's good. Change your equation. Now he's good. I think he actually matches the picture, hopefully. Question. Everything. What? It's 2 numbers. Silly. So we don't have to multiply this top guy by a number. I'd say multiply the bottom guy by a number, right? Couldn't you multiply him by 2? No? 2x minus 2x would cancel. Those are gone. Negative 4y and then negative 3 would be negative 7y equals negative 10 and 3 would be... Nice. But then negative 7 again, right? So y equals 1. Dun, dun, dun. And then we would plug back in. And long story short, x equals 3. Aha, I did get the right one. Nice. 3, 1 is the intersection. So long story short, for consistent, it just kind of happens. The math works out. You get an answer. It's finitely many. We're good. One solution, one intersection point, no big deal. What's the difference between this one, infinitely many, which is different than one solution, and the other one different from one solution, which is the inconsistent one? How does the math work on this one?
They're parallel, but they don't have the same.
Yeah, but how would the math turn out? We would multiply by negative 2, that cancels, right?
Why intersection?
Multiply by negative 2, except when you change it.
Yes.
That's how she's at.
I know. I don't know how these examples ended up like opposite. That's okay though. There, haha. We just need a negative, right? There we go. Okay, haha. Now what happens when we multiply by -2? That will be a plus 3y, which is going to cancel out, and then multiply by a -2, and that will be 0 equals -7. Ah, what's going on?
No solution.
So the difference between parallel lines and no solution is that you get a false statement, all the x's cancel out. And infinitely many, you get a true statement, all the x's cancel out. So both of them are special cases, the inconsistent and the consistent with infinitely many. However, they are very different. True leads to infinitely many, false leads to no solution, and if the math gives you an answer, well, no big deal, that must be the other one. Okay? Whew, that page was rough. There's enough to change it.
So if it's an equivalent equation that is consistent,
Yes. Yes. Good way to see it. If it's equivalent, it'll be consistent and infinitely many. Now let me get rid of this random hiding thing. In my notes I have things hiding from time to time, and then when you save it in this program, all my hidden things come out. Let me hide the systems. The very end, section 7.2, which we might need to continue a little bit tomorrow, but to be honest, I think we'll make it. It's just what happens or what changes when will a system be needed to solve a word problem? An application. When will a system be needed to solve a word problem or an application problem? What? There are systems on the SAT? Who would have thought? Yeah, probably. That's too thick. It's about the right color though. Fairly close. So long story short, this problem needs a system when you have more than one unknown, right? It's not just x missing, it could be an x and a y, or an x and a y and a z, or an a and a b and a c, or a who knows and a who knows and a who knows. Does the problem involve more than one unknown? You don't have to use x and y and z every time. And are there two or more conditions or equations that need to be satisfied? And those are telltale signs. Telltale heart, egg round. Oh. Anyway, telltale signs.
Hey, it's not
I said it's
Nice
telltale.
hide.
Thanks, in a kind of depressing sort of way.
It
Has to do with the heart, right?
was kind of like that one. What? Very easy?
That
Yeah,
was
my heart is absolutely
yes.
under my bed. Cut out and
Heart was beating his guilty conscience.
Well,
What?
It's like
well, that's something.
Sweet, gosh.
I'm just all about. I have my brain current.
Guys, we're still going. Breaking focus. I know, I shouldn't do anything else besides math. Math does not apply at all.
We'll get there
It wouldn't do.
Anywhere else.
You being distracted.
Yeah. All you just need to do is.
We have an application problem. You can figure out how to solve it. My hint is it probably has something to do with the system. An airplane flying into a headwind travels a 2,000-mile flying distance between Chicopee, Massachusetts, and Salt Lake City, Utah. New England has much. Way to make a cute name, not be cute anymore. All right, so. In 4 hours and 24 minutes, on the return flight, the airplane traveled the exact same distance in 4 hours. What? Time travel? How did that happen?
Magic.
No, not magic. You guys have been on airplane flights where it's longer one way than the other?
That
What
was
happens?
magic.
Or it's projected to be a certain time and it takes longer or slower, and that doesn't mean you're sitting on the fairway or the runway. You're actually in the air and it takes shorter. What happened? The wind. The wind what?
Helps or
Right? This one, if you're flying into a headwind, what does that mean?
slow.
It's slowing you down because it's pushing against you. So the plane's instruments are like, hey, you know what? We're aiming for this, and then the wind is like, we're slowing you down. Or I should say the engine is working, which should result in still, if there was no wind, it would result in a certain speed. But with the wind pushing against it, results in a slower speed. Anyway, the wind is working against on the way there, and it's working with on the way back. Huh. What are they asking for at the end?
The airspeed of the
Find the airspeed of the plane and the speed of the wind. So we don't know the airspeed of the plane. We call that P for plane. Okay. Then what am I going to do for the speed of the wind? We could do S. I was thinking W just to be like plane and wind, but either way works. Could do A and S for airspeed and speed. What else? Assuming that both remain constant. So we have 2,000 miles. That's a distance. We have 4 hours and 24 minutes and 4 hours. We have two different lights, right, guys? We have to and we have from. We can think of we have the trip away and the trip home. So, wait a minute. How do we put together distance and time and speed, which is rate? Rate, distance, time, rate, time, distance, rate. Is that a formula? Dirt! That's how I remember it. Distance equals rate times time. Dirt. It's a physics thing, but you guys should have seen it like physical science or I don't know. Distance equals rate times time. Distance. How far?
2,000 miles.
2,000 miles.
2,000 miles.
What was the distance on the return trip?
2,000 miles.
Same trip. Huh. Yeah, I know, it'd be a little unrealistic, right? But for sake of the problem, I'm just trying to keep it simplistic. Probably be a little bit different flight plan. But either way, distance equals rate. Rate
240
times time. 4 hours and 20. Wait. Can we put hours
240.
and minutes?
No,
We could, but let me just say, learning from experience, let's go hours instead. I know, you don't like it. 24 over 60 is 4 point what?
4.4.
So we have 4.4 hours over here. We haven't really been putting units, so I guess we'll stop doing dimensional analysis. There we go, just 4.4. Over here, rate times 4. Wait a minute. Can these two be the same if these are equal and those are different?
No.
No. So how do I put the rate here? What is the rate on the way there?
Oh.
We have these variables. How do we use them?
Yeah,
We have P and W, which is like X and Y, but are they working against or for? Together or against each other?
Against each other.
So the plane is saying this and the wind is saying, nope, I'm slowing you down. Right?
No.
How about on the way back? The plane is saying, hey, I'm going this way, and the wind says, sure, I'll help you. And they're saying, assuming that they both remain constant, this is like an ideal situation. In different classes, you would say something like in a vacuum, assuming there's no extra friction, etc. Now, how do we solve for P and W? I see a system waiting to happen, but what don't I like? Can I just divide?
Yeah.
I thought that would be easier. This one over here, we can divide by 4, divide by 4. It's a little easier when you divide by 4, right? Because then we'll go ahead and get 2,000 divided by 4.4. 154 point what?
454.
Oh, that makes a lot more sense. I'm like, that's crazy. 454 point
5, 4, 5.
equals P minus W, and over here we get 500 equals P plus W. What do you guys think would be the easiest way to solve?
Substitute or eliminate, get rid of that W.
Right? And we end up with,
E equals 500.
you could use substitution, I just kind of like elimination better. So all I have to do is divide by 2, right? If my 2's can actually look like 2. People in the front, we're a little too chatty today. Let's try to zero on in just a little bit more. What does my P end up equaling? My plane speed is 477.6 something miles per hour. And if I know P, the plane airspeed, what can I do? Do I have something to plug into?
Anything.
Sure I do. I can do that one, but he has 4.4. This one seems a whole lot nicer to plug into and solve. Okay, here's the long story short. I did say that we would spend tomorrow on 7.2 as well, but check it out.
Yay.
Oh.
So we can
So-
do homework.
Yeah, we can go work in class.
We're going to check 7.1 at the very beginning of tomorrow. I will see if anyone has questions on 7.2. If those of you who had 7.1 ready today, you can work on 7.2 tonight for tomorrow. People who are done with class, your notes are graded, pick up spirals later. Then we will start 7.3. Sorry, I'm trying to finish my thought. Bye guys, I'll see you later.
Bye.
Have a good rest of the day.
Thanks, you guys too.
Thank you.